That might be it.
No, that's not. The new one's back.
Okay, go.
Weightlessness at the top of the corkscrew. We're gonna do a prediction with Matt. Good.
So we just recorded the amount of time it takes to train from the beginning to the end. So now we need to go measure the length of the train so we can find the train speed.
Right. Just said what I was gonna say.
We're now going on the corkscrew so we can make our prediction.
Diane is a little bit excited. So am I.
Now back in the lab with our measurements.
On the velocity. Now for the centripetal acceleration, all I need is the radius. What's the radius? Tim! What's the radius of the corkscrew?
Nobody knows.
What?
That's it.
Hey, guys! I just gotta ask you something. Do you have any idea what the radius of the corkscrew is by chance?
How would I possibly know that?
Julian, I just have to ask you something. What's the radius of the corkscrew?
I don't know.
Julian! Oh. How can we make our prediction without the radius of the corkscrew? Rebecca was right. We are gonna fail. Rebecca's never right. Ever.
For the love of God, will you quit screwing up? I can't take it anymore.
Hello, Diane. What seems to be the problem?
Hey, James. Nobody can answer my question.
Well, the answer's simple. It's 7.4.
Well, I didn't even ask you the question.
Well, everyone should know that 7.4 meters is the size of the radius of the corkscrew.
James, wait, what? Okay. Well, now thanks to James Burgett, we do know the radius, which is necessary in our equation. We have to figure out the centripetal acceleration of the corkscrew. Where in the equation, you need velocity, which we do up here. Velocity equals distance divided by time. Distance of all the cars is 15.5 meters. And then how long it took for the first car to get to the top of the loop, from the last car to get to the top of the loop, was 50 frames on the camera. Since the camera uses 30 frames per second, we divided by 30. This gave us 8.611 repeating meters per second. Now, we can plug it into the equation. The equation is velocity squared divided by radius, thanks to James. We used 8.6, skipped the 1, divided by the 7.4 and gave us 10.6. What we learned from this is that you do not experience weightlessness on the roller coaster at the very top. In fact, you experience something very similar, but if you're experiencing weightlessness, you would be experiencing 9.8, which is the opposite of gravity. So there's our math.
Diane and Rebecca on the corkscrew to test our prediction using a vertical accelerometer. What is a vertical accelerometer, we ask? This is the vertical accelerometer. This will measure the vertical acceleration on the corkscrew once it goes upside down. This is 0G, 1G, 2G, and 3G. At regular acceleration, the ball hangs at 1G. We will use this device on the corkscrew and we'll see how it works. Now back in the lab for our final conclusion.
As you saw in the video, when we head into the turn of the corkscrew, there's a strong downward force and the ball goes all the way down to here.
The ball goes up to 0G when the ride goes upside down.
But I thought we had a downward force on you. That's what our calculations said.
But because the force is so small, it may feel like weightlessness, but it actually is not.
Oh.
Which is why it's my favorite ride at Valley Fair.
I get it.
Yeah. We are the physics masters.
Boy, were we excited. We had our goggles on, but we couldn't find the corkscrew.
And a special thanks to...
This is Travis. He's our camera guy. He's awesome.